so I'm Kwaku, and I'm a former consortium that includes André and Centre in Norway, Trinity College in Dublin, and University of Rennes in France. And I'm here to talk about emergent robustness in software systems through decentralized adaptation and ecologically inspired ALife approach. It's a really long name, and I apologize, I wave my hands a lot, and so don't be surprised, there's no magic involved here, it's just me waving my hands a lot. Anyway, so this talk is kind of going to be divided into kind of three main parts. I talk about the background, I give you some motivation, and then I describe the system and some experimental results. So first of all, some background. So, this is a map of the internet network. This is from circa 2005. As you can see, it's basically snaps out the links between different entities on the internet. It's a really large, huge network. Its network has been evolving. It's evolving. It's very nodes come and go, links come and disappear, and software systems have been built on top of this network. So software systems currently are kind of built as loosely coupled software systems. So basically, providers provide services, and consumers which rely on these services. And links come in and go in, and entities come in and go in. So, to the right over there is an example of a software system. Basically, you have all these entities that are joined in different configurations. Now, these software systems have to deal with the uncertainty and unpredictability of the internet. And currently, they do it through approximate redundancy, where basically you basically provision a lot of services or a lot of platforms to kind of provide everything and hope you have more than enough, and you're not really sure whether it's going to be enough. So it's sometimes overkill or underkill, and you're not really sure. Or you try the centralized management techniques where kind of like Google, where you basically just monitor everything and basically have this global view of everything. Now, this is kind of, if you're Google, it's good enough. You can monitor everything, it's good, but not for everyone. It's kind of not really good. So we say we must adapt. Now, why must we adapt? First of all, there's this thing from Alice in Wonderland. I'm sure a lot of you have read this book. There's the Red Queen, one of the main characters. She says to Alice, "Now here you see, it takes all the running you can do to keep in the same place." Basically, kind of in essence, just saying that you have to actually keep evolving and adapting to just maintain the position you are in that evolution landscape. And so basically, kind of analogize this to software systems. We're kind of saying that in software systems, in order for software systems to cope with this unpredictable uncertainty in the network, they have to basically kind of adapt and evolve, kind of just to keep providing the same services that they've provided. Or else, they kind of leak and loss of downtime, unable to provide all the services that you need. Kind of lots of you're not able to do what you're supposed to do. So basically, we decided to adapt this Red Queen hypothesis to software systems, and we came up with this target hypothesis of what this whole work is about. Basically, that localized adaptation can result in increased robustness. So first of all, in order to basically test what it is, we first had to kind of have a system in which we can kind of test our hypothesis, kind of test our analyze, and kind of figure out what we're doing. So we first, we took this advice from Stephanie Forrest, who's one of the very big people in network and in software engineering. She said, software systems can be better suited and controlled as when you view them from the perspective of ALife systems. So we kind of took this to heart and basically decided that we're just going to model software systems as an ALife in an ALife simulator. Basically, use this simulator to model evolution and adaptation in these systems, and then kind of figure out what evolution and adaptation strategies affect what they do to the robustness of the system, and how we can improve or maybe decrease the robustness of a software system. So now I present our ALife simulator. It's called EvoServ. It's a really, really terrible name. I think I didn't name it, someone else did it for me. But so basically, it's an ALife model simulator. You have providers and consumers as individuals in the system, and basically model the interactions between them. Now, software interactions between software systems are kind of like, they're software, like as you saw from one of the previous slides, providers provide some things and consumers provide something. Now in order to kind of remodel that well, we basically decided to do this through a bipartite graph model. And this is like a bipartite graph model. So basically, you have the consumer, provider, the provider provides a service, consumer requires it, consumer connects to the provider to get that service, and a pretty simple model. Now, alright, so this is kind of the basic model, graph model of the EvoServ ALife simulator. Now, first of all, I have to talk about adaptation and evolution in this system. Now, I want to distinguish between adaptation and evolution. So adaptation basically is kind of like changes that modify the composition of the individual nodes. So adaptation, each individual kind of modifies itself. It modifies its composition and what it can do. But these changes do not actually modify the global outlook of the system. In comparison to where we have an evolution where changes actually modify the state of the system. So individuals can come and go, nodes leave, links disappear, kind of the composition of the graph itself is actually changed drastically, can change drastically. Okay, so now that I've explained that, I'll explain our experimental protocol. I'll come back to this and actually explain what adaptation and evolution strategies that we kind of look at later on. But first of all, just give it like a brief review of our experimental protocol. So, we have this graph full of different software systems of providers and consumers and the services they provide. We basically just run our strategies on them, kind of run these different adaptation and evolution strategies on them, run them for a certain amount of cycles, and then we evaluate the robustness of the graph, basically tell us how well, the strategies affect the system. Now, you might ask, what exactly is the robustness of the graph? So it's basically kind of robustness, and simply just means how well does the graph resist perturbations. Now, in that sense, so if you look at this, x-axis is basically the number of providers, and y-axis is the number of consumers. And at time 0, you have this, where all consumers are alive, providers are alive, and as you kill more and more providers, the consumers die. And so we basically kind of just measure, we kind of measure the area under the curve. That's kind of the normalized robustness index, kind of telling us how well this network is, and how resistant it is to any kind of perturbation. So I'll give you a concrete example. So you have this network, C1, C2, C3, C4 consumers, and P1 and P2 are providers, and they provide P1 and P2 provide these kind of services, and C1 and C2 provide these services, and so they're all linked together. Let's say P1 disappears. Okay, so some of these links are gone. So now C4 doesn't have anything and kind of dies out. P2 goes, these two don't provide anything, and so they die out. And so basically, you measure this is how we measure robustness of the network. So basically, how long it takes and just how well this network can resist to things leaving. Now, in order to actually test the robustness of this network and actually test our adaptation strategies, we kind of have to tune it and make it very realistic, kind of make it similar enough to what a real world system is. So in order to do that, we basically decided to basically just collect some data on two large scale software systems. So WordPress, blogs, and web browsers. So basically we basically analyzed the top 500,000 websites on the internet, and a fifth of them, basically 110,000 of them, run WordPress. So we basically took WordPress, kind of scraped all of them, analyzed the plugin usage. So basically each blog basically uses a lot of plugins. And so we collected a number of plugins for each blog and kind of did some analysis on that. We also did this for web browsers, where we set up a website called myuv.org for a different project. But this is a browser fingerprinting website. So we basically collected statistics about the browser the different fingerprints of different users who visited this site. So basically, we collected data about fonts, plugins, fonts, plugins, user agent, different things. Basically, everything that your browser tells us about it when we you visit a website. We collected all this data, and using this, we basically kind of like just came up with the distribution of plugins used for WordPress and plugins used in web browsers, and distribution of how spreadable this is among the users of WordPress and web browsers. We actually found a pretty similar, consistent distribution among this. So basically, we found out that the number of plugins per each entity actually follows a Poisson distribution, and the rate of usage of these plugins by each user kind of follows a negative exponential slope. Basically, we just kind of like confirmed that we kind of compared this actual data to some other data that we looked online and found out that we actually using this as a source of data to tune our network was correct, because we were able to like mimic exactly the kind of distributions that people had seen in other networks that were similar to these different internet networks. So basically, we kind of then used that to tune EvoServ. So basically, we just kind of generated a set of different number of graphs. So a random set of graphs. We generated 50 because we found that after 50, doing experiments on more than 50 graphs, the results didn't really vary. There wasn't a huge variance. The variance was like less than 0.01, so it's good enough. But basically, so these are the kind of distributions of that. So like in the top left, so we have like X is the number. The top left is basically the services required by consumers. So X is count and Y is the number of times services required, and that's the distribution for that. The top right is basically a graph showing the distribution of consumer sizes. So, and bottom right is basically the links per consumer. So now I'm going to actually present the strategies that we investigated on these networks. As you remember, adaptation is varying the set of varying the individual nodes, but not varying the general composition of it. So basically, for adaptation and for consumers, you vary the set of links that you actually make to a provider provides service. So you kind of vary that. And for providers, it just means varying the set of services that you provide. So now I'm going to actually present the different adaptation strategies that we investigated and the ones that we found out. So basically, the first one, so here we go. So for providers, the providers are the bottom layer. So they're the ones who are providing things. So we're changing the set of services offered. And for each, since these are localized adaptation strategies, for each producer, you actually don't know. You don't have a global overview of this, of the whole network. You basically only know what your consumers do. So you know the number of consumers that are connected to you, the services that they require. That's kind of all the information that you have. It's a pretty simple, localized kind of view of this whole network. You only know what is in your neighborhood in essence. So for the first provider adaptation strategy, basically provide a new service or drop a new service. Basically, you can only drop a service if a consumer who's connected to you does not require a service. So, and as we don't want to, as a provider, you can't just willingly drop a service. A lot of people depend on it. You can only depend. If it's not used, then you can drop it. If not, then you can't. The second strategy we call it the popular adaptation strategy. Also a very terrible name again. But so in that sense, basically, a provider basically kind of changes, varies its set of services based on how popular or unpopular the services are. So popularity depends on, again, how used services are by the consumers attached to you. So, for example, these are some valid adaptations for producer 3 who's connected to A4 and A3, basically. So, you can drop 3, you can add 0, or you can add 4. Okay, so now I'm going to move on to consumer adaptation strategies. So consumers, again, are the top layer of that, basically change the set of links to providers, and so for consumers, you can also adapt willingly. You basically have to always have the services that you require being provided, because if you're not having the services provided, you're kind of dead. You're not really working. There's no point of you existing. So since this is also localized, these strategies are all localized. This kind of the consumers actually are only aware of a subset of providers. Now there are a lot of different service discovery mechanisms. There's lots of papers. There's different conferences based on that. And there's a new committee based on that. We didn't actually want to duplicate millions of them, so we basically just chose a random one where basically we just say your neighborhood of things that the providers that you have access to at a certain time. It's just a random subset of that population, of the entire population. So okay, here they are. So for the random adaptation strategy for consumers, you basically just choose to link to a new randomly chosen provider from that neighborhood. Then the second one is equitable adaptation strategy, where you try to maximize your equitability. So equitability kind of refers to kind of the provision of the services that you have. So in a sense, you're trying to maximize the number of times that your services that you require provided. Kind of the more simplistic way of seeing it is that you're trying to make sure that just in case one of the providers that you're connected to disappears, you can actually you have backup links to other providers that provide those services. So, give an example of this. So with a neighborhood of these three, of these P0, P2, and P0, P2, and P4, A1 basically, A1 requires 0, 1, 2, and 3, and the first line right up there is its current equitability. So it can actually connect to P3, increase the equitability, or disconnect from P2 and disconnect to P3, so P0 and P3. Okay, so these are basically just the simple adaptation strategies that we investigated. We didn't want to get too complex. We didn't want to kind of go overboard. We just wanted to investigate what exactly, validated adaptation, what an adaptation, localized adaptation is good, and these were simple enough, and could always do that without having to go overboard. So now let's talk about evolution in EvoServ. So evolution, basically, as you remember, is basically varying the composition of the network of the whole software system network. So this kind of involves, some entities reproduce, they can die, they get crossover, mutated, and these kind of there are analogies to this in software engineering. So you have applications that merge, like libraries that merge. You have you kind of combine services. You can actually just change, a server can actually an API can stop offering, and something can merge another API. So these are all analogous to different kind of mechanisms in software engineering. Now, for evolution, when you're evolving, previously, as I said before, the adaptation strategies, adaptation, you kind of want to make sure you're still always providing, you're still always kind of maintaining the number of, maintaining the availability of things. So providers can't actually kick off anyone just randomly and produce it. Services can always need to have their services. Consumers always need to have their services provided. Now, for evolution, we just decided no, it's evolution, and kind of in the real world, evolution means services appear, things come and go without actually paying attention to the links. It's a wild network. It's uncertain, it's unpredictable. So you can't actually guarantee that dependencies are always going to be fulfilled. So we decided to model that. So for providers, provider can go extend. Each provider has a 30% probability of going extend. It can clone itself. 30%. Can reproduce. 30%. So kind of you reproduce by you can clone yourself and then mutate the services that you have. So when a new 8 minutes? Two. Okay, super. Okay. So you basically can randomly mutate all the services. So every service is a 20% chance of being mutated, or you can actually have one that's based on how ecological systems work, where basically the probability of a service being taken away or kind of being mutated is based on how popular it is. I mean, this is kind of based on ecology, basically kind of trying to mimic environmental pressure. So for consumers, again, you can go extend the same probabilities, you can go extend, you can clone yourself, you can reproduce yourself. When you reproduce yourself, you basically kind of just, there's another consumer. You kind of just get a subset of the services that both of you, the two parents provide, you combine it, that's a whole new consumer. So basically, as again, evolution is just basically kind of to these strategies just to kind of like vary the number of nodes in the network, kind of simulate things coming and going and leaving. So we decided to run all of this on our graph and on the EvoServ, basically kind of like model basically how all we deal and kind of figure out the robustness. Again, the baseline basically is you have a network that doesn't adapt or evolve. It's just baseline. So basically, this is in comparison to that. So basically, x-axis is adaptation stats, and the y-axis is basically the unnormalized robustness. Now you can see line in blue is when both consumers and providers kind of randomly just pick, service to mutate or to drop a hard, or consumers just pick a random provider to connect to. And that's low as baseline, and robustness again 33.4% better than just not doing anything at all. Then the next step, did you see that? Well, is when consumers do the random thing and providers use the popular adaptation strategy, and that is 35.9% better than just not doing anything. And then Equitable, where consumers basically kind of like evolve, kind of based on their local, they kind of look a lot of that, and it's based on popularity, and versus providers is randomly evolving. That's 37% better than baseline. And then we have where consumers actually, consumers use the Equitable one and providers just use the popular one. So both of them are actually kind of doing this based on probabilistically based on what services either the consumers require or the providers provide, and that is 46.2% better. So as you can see, when you actually just take into consideration local information and kind of like actually probabilistically work in that, you can actually you're much more robust. So then we decided to ask, so what if we basically just this is basically the standard line when there's no nodes leaving or evolving, there's no evolution, so nodes are not leaving, there is just a static network. What if we kind of allow evolution? So when we allow evolution, we kind of basically had the similar results, like similar results where it was just basically the same exactly like this, where where if both when the last line, when both of you are actually taking into consideration the fact that you're taking into consideration the popularity of in your local network, it does better than everything else. And then we decided to ask again, so number 3, what does the distribution of services in this graph, like does it kind of change, like is scarcity, does it affect this network? Again, we tried it and we again found out that our localized adaptation strategies do better again, and they do better and kind of in the same order, ranking order, they do better in the same way. And then we decided, what about the scale of the system? So what if we relax or increase the scale, like kind of try from 100 consumers to 5,000 consumers to 50,000 consumers? Again, we have similar results. So in essence, like our conclusion is basically that our localized adaptation strategies are better than the random baseline, better than the random baseline, better than not doing anything else. We can definitely introduce local robustness, and it's the strategies are robust to parameters of the graph and to evolution, and they look like, so they're basically local information. There's no need for this centralized overview or anything. And we found out for the equitable popular local adaptation strategy is actually the best, which is so when both of you are combining localized adaptation strategy to actually look at popularity of services, you actually do better than anything else. So there's one final question: is robustness and emergent property adaptation in software systems? Now, a few people have been saying, well, this is true in other systems, but not in software systems. But our results say resoundingly, yes. It is true. You can actually, robustness emerges from this localized. Just from this having a local overview without having a centralized view, you can actually have a better robustness than just having a global view. So again, so finally, so we basically also presented this EvoServ software. It's actually online. It's open source and online. We see it's useful for testing evolution, adaptation software systems, and we think other people will find it good to use. And our data is also online, so other people can use this. And it's actually useful for other things, and we're using for other things. So it's available if anyone needs to check it out. And yeah, that's it.